Good morning. We are Cesare Sposito and Francesca Scalisi, and we present a research entitled Circular Economy and Built Environment: Research and Good Practices for Environmental Sustainability. The subjects of climate change, excessive use of soil, renewable sources, ever-increasing production of waste and demolition waste have, in fact, entered our daily life. The building industry is one of the main causes of these subjects, as it absorbs about 40% of the total energy consumption in European countries and produces about a third of total waste. The total energy used in the life cycle of a building is determined by the embodied energy and the operational energy. Studies and research have shown that about half of the environmental impact of buildings during the whole life cycle is determined by embodied energy, since many building materials are produced with fossil fuels and their derivatives. Hence, the need to optimize the overall environmental performance of new buildings, mostly by assessing their embodied energy and their impact on the whole life cycle. The traditional linear approach that in building practice translates into take, make, consume, waste has been identified by several researchers as the main cause of the impoverishment of non-renewable resources and waste production, thus defining building activity as one of the most unsustainable man-made practices for the planet. Principles and applications of the circular economy in response to the urgent need to reduce environmental impacts and an efficient use of non-renewable resources are starting to attract the interest of the construction world, thanks also to the studies carried out by the Ellen MacArthur Foundation, which has identified 6 areas of action called RESOLVE: regenerate, share, optimize, loop, virtualize, and exchange, for business and countries aiming to shift toward circular economy, to reach sustainable development and to safeguard future generations. This paper wants to make a contribution to the understanding of the state-of-the-art on cycle-based research activities, experiments and creations that the building industry and the academy have implemented in recent years. The research actions operating on a circular basis on the built environment are divided into 3 levels: macro, about city and neighborhoods; meso, about buildings; and micro, about materials and components. An example of circular intervention on a macro scale is the Queen Elizabeth Olympic Park in London, which, involving the whole Stratford district, has been compared to an urban regeneration project. The Olympic Stadium was designed by optimizing its building system, anticipating a later transformation of the structure at the end of the Games as a stadium for a local football team, and anticipating the reuse of about 95% of disused building materials and the recycling of 50% of materials otherwise directed to the landfill. Beyond the characteristics of the project and the technical solutions implemented to reach the intended purposes, we must underline the social consequences that in 2014 the London Legacy Development Corporation, in charge of the transformation, was able to generate. Just to name a few, the company supplied to over 40 neighborhood associations materials and disused components that they needed, but also Hub 67, a community center of another district, Hackney, that fosters social projects for citizens, young people, and schools, made 80% with materials coming from the Olympic Stadium. For the mesoscale, another project worth mentioning is the renovation of the Leander in Duiven, the Netherlands, 2015. The electricity company has transformed its headquarters into a sustainable building capable of producing more energy than that consumed by 24,000 square meters and 1,500 employees, becoming the first renovation project in the Netherlands to obtain the BREEAM NL sustainability certificate. Besides the different actions that have led to reuse 80% of the original surfaces and to use up to 93% of materials according to a circular logic, the elements that characterize the intervention is its large roof, which connects 6 pre-existing buildings designed with the technical support of a business that had acquired its know-how from building roller coasters and has managed to optimize the structure, making it lighter, reducing the use of raw materials, and providing nodes and connectors that facilitate the disassembly of the roofing so that it can be reused. At the microscale, the BioBuild panel, structural component to cover facades in biocomposite, sums up the philosophy of the circular project, and it demonstrates how circularity can be achieved by using alternative, innovative, and bio-based materials. Funded by the 7th Framework Programme of the European Union for Research and Ecological Development since 2015, BioBuild has already been responding to the need to reduce the embodied energy and the cost of production compared to traditional solutions that use non-renewable raw materials. The panel is made by the combination of natural fibers extracted from flax, hemp, and jute plants, and biological resins derived from the residues of sugarcane and soybean harvesting. Obtained from fast-growing plants, regenerating in short cycles of 3 to 4 months, and from residual agricultural waste, has a density of 1,200 kilograms per cubic meter, which make it lighter and more resistant than panels made with traditional oil-based composites and aluminium, and is characterized by a thermal coefficient of about 0.2 Watt per square meter per Kelvin, which facilitates the elimination of thermal bridges of facades. The most significant data is the embodied energy. It is reduced by 50% compared to panels with similar performances, but made with aluminium or oil-based composites. All system components can be easily disassembled and recycled or reused at the end of their life cycle. Current scenarios for the end of life include shredding the biocomposite, consequently used as mulch, or incineration. In construction, the concept of looping can be applied by implementing the 3 R's: reduce, reuse, and recycle, and in particular through the use of recycled materials or the use of dry construction systems through prefabricated elements and components according to the design for disassembly principle. In literature, there are many studies that have investigated how each option affects the global warming potential, resulting more sustainable than traditional buildings on an environmental level. However, the results are often conflicting. In fact, some researchers report that recycling is the most widespread practice, while others classify recycling as the least effective among the 3 R's, since some of the materials to be recycled do not get a second life or are contaminated in the transformation process. Other studies promote design for disassembly and its reuse in more life cycles, since it can reduce demolition waste. However, they agree on the low marketability of its components once they are used. The first study was carried out by Rasmussen, Birkved and Birgisdottir. They compare two different projects, both composed according to the Danish regulation, that have used different strategies. One, the recycle of materials strategy, the other, the prefabrication strategy aimed at disassembly and reuse, to evaluate which one is the most sustainable for embodied energy and produces the lowest environmental impact on a long-term period of 120 years. They used the LCA analysis method according to the European standard EN 15804 and EN 15978. The results of this study are quite interesting. However, at first, it appears they do not provide indications for making a clear choice between the strategies. In fact, in the building made with recycled materials, the production phase has a low environmental impact, especially if the construction includes wood products with a negative global warming potential. While during the replacement and end-of-life phases, with the incineration and release of stored carbon, there are significant impacts. Opposite values are found in the building following the design for disassembly philosophy. In a nutshell, global warming potential values of the two buildings are almost equivalent. For the first case study, it is 4.7, while for the second it is 6.7. This last parameter is reduced to 4.3, considering the reuse in the next product system, amounting to 2.4. Another interesting study was carried out by Eberhard, Birgisdottir and Birkved on an office building. The whole construction and also the reinforced concrete structure was designed according to the design for disassembly philosophy. In this case, the three Danish researchers, using the LCA method in line with the requirements established in the EN 15978, have taken into consideration, beside the global warming potential, other impact indicators, which may be less common but still important for the environment, the use of resources and the toxicity of materials. Two possible life cycles, lasting 50 and 80 years, two subsequent product systems, and four options in which the reinforced concrete structural elements, which make the largest percentage of the mass of the building, are replaced with steel and wood elements. The study reveals that the extent of the environmental impact savings caused by the different systems varies according to the input categories and the scenario considered. In fact, the configuration of the material has a significant influence on the embodied environmental impacts of the building, and depends both on the number of reuse cycles of the components and on the duration of the material and the life cycle of the building. Therefore, the optimization of one group of components to reduce the single environmental impact potentially may not necessarily benefit to the overall impact level of the building in the same measure. Similarly, the study does not clearly report which scenarios, options, or materials should be chosen, while it considers realistic that the potential impact savings of the design for disassembly building can be substantial in the third reuse cycle. In conclusion, we are still at the beginning of a long path heading towards a historic transition. From the research described, it appears that the option provided by the design for disassembly buildings prospects benefits that are equivalent to the first option, but at the end of a time span of 50, 80, or even 120 years. This would entail the probable risk that the modeled scenarios may be far from the reality of that moment. In theory, it is like we acquired a certain environmental credit that we are not sure we will be able to collect, because future scenarios are not certain and predictable, and also because any changes in use and functions of the building, new problems due to global warming, different waste disposal and recycling systems, different energy sources. Conversely, this strategy could be chosen compared to the observed global warming potential values if the elements and components could be disassembled and reassembled in more than 3 product systems and in shorter cycles. Ultimately, in order to close the loop of matter, the built environment has to be rethought with new design strategies, innovative business models, a new relationship among different actors of resource management. From the reference literature emerge 6 fundamental dimensions that can affect and condition the transition towards the circular economy. The role of politics, the economic dimension, the environmental dimension, the behavioral dimension, the social dimension, intended as sharing economy, and the technological dimension. The latter includes both the management and storage of enormous amount of data that the circular process requires, and the numerous technological innovations useful to the production as, for example, the aforementioned 3D printing. Thank you for your attention.